Relationships involving heats of reaction. Okay, let's remember, heat of reaction is an extrinsic property. It depends on the amount of stuff. So, if we multiply a reaction by a factor, we have to multiply the heat of reaction by that factor as well. So here's an example. Carbon plus oxygen forming carbon dioxide. The heat of reaction is minus 393.5 kilojoules. This is an exothermic reaction. It's giving off energy, right? If we double the reaction amounts, because this is for 1 mole of carbon. This amount is for 1 mole of carbon. If we double the amounts by doubling the coefficients in the reaction, then we have to double the heat of reaction as well, because this is for the amount specified in the equation. Does that make sense? If the reaction is reversed, if we swap the reactants and products, write it backwards, then the sign gets changed. Because if carbon reacting with oxygen to form carbon dioxide gives off energy, that tells us that the product CO2 has lower internal energy than the reactants. If we do the reaction the opposite way, then everything's opposite. And if we take carbon dioxide and decompose it into carbon and oxygen, that's an endothermic process. We have to put energy into it. Does that make sense? If these concepts make sense, then they're easy to remember. If they don't make sense, it's kind of hopeless, almost. Not quite, but almost. We also said that the heat of reaction is a state function. Doesn't depend on the process, just like a change in elevation. Doesn't matter if you go the windy road up the mountain or if you hike straight up the mountain, the change in elevation is the same. The change in enthalpy is the same regardless of how you get there. So you can decide to get there however you want. So if we can express a reaction as a series of steps, then the heat of reaction for the overall reaction is the sum of the heats of reaction for each step. Does that make sense? It's like, I guess, a little like partial pressure in that you're adding things up, a little bit. And this is known as Hess's law. The change in enthalpy for a stepwise process is the sum of the enthalpy changes of the steps. So if you think maybe not of climbing a mountain, but of going up and down some stairs. And, let's draw a picture. Oops. I remember going to try on shoes as a child and being just fascinated by these things they had at the shoe store. Did they have those when you were growing up? They're these little stair things, and they wanted to see you go up the stairs and they could watch how your shoes fit or something. I don't know. Okay, whatever. So if we're starting here, let's call that A, and this is B, where we're ending up. We can describe this change in height as this change plus this change, right? Or it could be going up here and then coming back down here with a positive change and a negative change. This is the idea that we're talking about here. It doesn't matter how far up and back down and maybe multiple steps up and down that you went. You start in one place, you end in one place. The change in height is the same, and it is equal to, I'm pointing in the air, they can't see that. It is equal to whatever you did up and down on this silly little staircase. Does that make sense? It wasn't great, but that's what I got today. So with a reaction, if we can describe, so here's the reaction that we're interested in. is going from A plus 2B to 2D. If this can be described as first going from A plus 2B to C, and then from C to D, because perhaps these are things that we could measure, but this one we can't measure for some reason. We can figure out what this change is by adding these changes together. Does that make sense? So here we've got a positive change in enthalpy and a larger negative change in enthalpy, and you add them together and you get this total, which is a negative change in enthalpy. So it's just adding. So these sorts of problems, I guess if your brain works in a certain way, these are fun, and if your brain works in the other way, I'm guessing they're not so fun. But let's look at this. We're supposed to find the heat of reaction for this reaction. We're not given calorimetry information or anything, but we're given these equations with these known enthalpy changes. So what we have to do is figure out how could we add, subtract these equations to end up with this. Okay? And this is kind of a trial and error sort of a deal. So here we want to end up with NO as a product. So let's look at these. This one has NO as a product. That one has NO as a product. We've got N2O as a reactant. So we try to find that one in here. This is the only one with N2O as a reactant. So we're going to need that one for sure. So I'm going to write that one down. We've got 2 N2O. I'm going to ignore the state symbols for now. I wrote that exactly as it was given. And so I'm also going to copy down delta H exactly as it was given. This is where those other ideas of if you multiply or you flip it, you need to change delta H accordingly. Okay, so what else do we have here? Well, so this is making nitrogen and oxygen. Our overall reaction does not have nitrogen and oxygen as a product. So we need an equation in here that has nitrogen and oxygen as a reactant so that we can essentially cancel them out. So this is a lot like adding algebra equations. At some point you learned how to solve two equations find two unknowns with two equations. It's the same kind of an idea here. So I want to use this one now, and I'm going to put that one in here because then I'll have N2 and O2 on one side as products and N2 and O2 on one side as reactants. So I'll put that one in here. N2 plus O2 is going to give me 2NO. And that one I didn't do anything to, so I'll just copy down its delta H as well. Plus 182. Do you have to write the plus there? No, you don't. But it can be helpful because it's intentional. You didn't just forget the minus. Okay, so if we were just adding these two reactions, one of these nitrogens goes on to react with the oxygen to form this. And so this oxygen is that oxygen that reacts. And one of those nitrogens is this nitrogen that reacts. So it's a stepwise thing. So the N2O, two N2Os made two nitrogen molecules and one oxygen molecule. one of those nitrogen molecules and one of the oxygen molecules went on to react to form two NO molecules. That always looks like no to me, but, right? Okay, so we're making some progress here because this is what we're trying to get to. We've got N2O on the reactant side, and now we've got NO on the product side, but we've still got a nitrogen in here that doesn't show up over here. And we need to have NO2 in there. And so we've used this equation, and we've used this one. So it's probably time to throw this guy in there. So this one has NO2. In our final reaction, we want NO2 to be one of the reactants. So we need to take this one and flip it backwards, reverse it. So we're going to write 2NO2 makes 2NO plus O2. When I do that, when I reverse it, I need to change the sign of delta H. So instead of being minus 113, now it's plus 113, because it's going in the opposite direction. Okay, so now we've got N2O and NO2 on the reactant side, and we've got NOs on the product side, but we've got this oxygen here. So, and we've got this nitrogen left over. So what we need to do is we need to take this equation and we need to put it in there twice. So I'm just going to multiply this by 2, multiply the whole equation by 2. So I already crossed off the first nitrogen. This would be the second of those. This is 2 nitrogens now, 2 nitrogens. That's going to take out both of those 2 nitrogens. Now this is 2 oxygens. Well, I took out one here, but it's going to take this one out as well. Does that make any sense? Not really? Okay, that's fine.
Does it matter what side of the reactant or product to cross them out?
It does matter. If you have something on the product side that is the same as on the reactant side, they get crossed out. So think of it this way. I've got 2 N2O molecules. They make 2 nitrogen molecules and 1 oxygen molecule. So one of these nitrogen molecules and one of the oxygen molecules inside the parentheses here got together and made 2 NO molecules. I don't have these anymore. They reacted and became something else. Let's see.
So each equation has to flow into the next one?
They flow together. I'm trying to show you the process. Jeez. Come back to me. There it is. I'm trying to show you the process by which you would figure out how to combine these. Because there's no, I can't just say, we'll just add them together, figure it out. That's not real helpful. Right? So I'm trying to show you the process of how to think about how to put these things together. So let's try to think about it in a little more of a linear form. So that first reaction, 2N2O made 2N2 plus O2. I'm trying to figure out how to get from here to here, but these are the steps I'm limited to. So I can't just go directly from one to the other because I don't know the heat of reaction for that. So I'm going upstairs, I'm going downstairs, I might be going down again and coming back up in different increments to get where I want. So if that's our first reaction, then we can see from this reaction that these two guys can go on and make 2NO. But I had two N2s here, and so I still have a nitrogen there. Okay, so I'm going to take that off, and I'm just going to write there's two of them there. You see that? So there's the two N2s. One of the N2s and an O2 went on to make that. Well, what's the other N2 going to do? Well, we don't know yet. Then we throw this other one into the mix. One of these days I'll learn that you cannot write with an eraser. So we'll throw that in there. And then these two guys are going to make 2 NOs. Is this helping at all? No? So this reaction made this nitrogen and this oxygen. You with me on that? This nitrogen and this oxygen reacted to form this. Do these two molecules exist anymore? No, they don't. So I'm going to cross them off. They reacted and turned into something else. From that first reaction, though, there was a nitrogen molecule left. So I throw this one in here. 2NO2 forms 2NO and 1 oxygen. So now this nitrogen and that oxygen can make 2 more NOs. You with me? Okay? You're like, okay. So those guys are gone now. They reacted and they formed 2 NOs. Right, so now I've got this one, and I've got that, and I've got that. That's 6 of them.
Okay, so then you add the heat,
So let's
joules.
stop here and write down what we have left so far. So I've got 2 N2Os, that was the reactant, and another reactant was 2 NO2s. And those are forming, I'm going to lump all these guys together, right? That's 6 NOs. So this is very much related to this, right? It's just doubled. So what did I have going on here? I had this first reaction, 2N2O going to nitrogen and oxygen, and I wrote down its enthalpy. And I've got this one, 2NO2, and goes to 2NO and the H and the O2. That's this guy down here, which I had to reverse from up here. And when I reversed it, I changed the sign. Then we had this process in the middle, the N2 plus O2 making 2NO. So that's this guy. But then that happened again using these two guys. So I double that. When I double that, I have to double this. Because that happened twice. Okay? And my bottom line of what's left over is this, which is 2 times that. So the way we normally show this is we take this, we're adding all these things up. Maybe I'm going to undo the X'd out things. Because I think maybe that was confusing. I don't have as much experience showing these sorts of things, explaining this sort of stuff. So you'll just have to bear with me. Now I've lost myself. Oh, this was an O2 over here. And this was 2 N2s. Okay, did I get that back okay? So when I add all these things up, I've got 2 N2Os. Let's just do it the long way. 2 N2Os. And I've got 2 N2s. And I've got 2 O2s. And I've got 2 NO2s. It's like that's an awful lot of 2's and N's and O's, right? So what I've done here is I've taken everything to the left of the arrow and I wrote it down. Then I'm going to write down everything to the right of the arrow. So I've got 2 N2 plus O2 plus 4 NOs because this whole thing was multiplied by 2. So 2 times 2 is 4 NOs. And then I've got another 2 NOs and an O2. Does that make more sense? Okay. So we're all learning. Well, this could be simplified a little bit, right? I could put these O2s together. So I'm going to take this guy and put him in here. I've got 2 O2s. And here I've got 4 NOs and 2 NOs. Well, that's 6. Loud no's, right? Because caps are yelling, right? So that's an N. Okay, so I'm combining like terms. We can think of these as variables. I'm just combining like terms. And now I look and I see over here, I started with 2 N2s and I'm ending up with 2 N2s. Those are, you could think of them as spectator ions, I suppose. But what's really happening is they're being consumed. And the same thing with these oxygens. And so what I have left is what I wrote up here. Now, the total delta H for that is the sum of these things. So I've got this one, which is negative, this one, which is positive, and I have to multiply it by 2, and this one, which is positive. And so I just get out my calculator, and I've got negative 163.2 plus 2 times 182.6 plus 113.1 equals. So delta H for this reaction as written is 315.1 kilojoules. I'm going to bring that up here. 315.1 kilojoules. Is this the reaction I was asked to find delta H for? No. I need to divide all these reaction coefficients by 2. If I divide that by 2, I need to do the same thing to delta H. So 315.1 divided by 2 for the reaction as written here, delta heat of reaction is 157.6 kilojoules. Fun? Yeah. So people who like logic puzzles may find this amusing. I would expect most people would not find that fun.
You can navigate on family road trips.
Mm-hmm.
Is it an interesting journey?
Well, we don't do our journeys like that. We tend to go more of a straight line. But yeah, I'm the one that can keep straight where we're going. And my husband's like, I don't know, he just drives.
So you just looking at the three earnings, you just want the NOs to be on the right and the majority of the NO2.
It's kind of a trial and error process, like balancing an equation. You may try something and realize, oh wait, that's not going to work. Okay, that's the error. Then you try something different. But the clues that you have are you want to end up with the reactants on the reactant side and the products on the product side. And what you can do with these given equations is you can reverse them and you can multiply them by things. You could multiply them by 1/2 if you needed to, or some other fraction. You can multiply them by a number. Just remember that whatever you do to the equation, you have to do to delta H. If you flip the products and reactants, then you flip the sign.
When we have a question like this, those equations and their kilojoules are always going to be given.
Yes. If you were given a question like this on an exam, you would be given all of this information. And this is all the information that is needed. You don't have to go look up anything. So, why do we do stuff like this? Well, there are some reactions where the heat of reaction can be measured experimentally. There are other reactions where it's really, really not practical to do that. But we can figure out the heat of reaction by adding up reactions where we know the enthalpy change and end up with that. And why do we make you learn this? Because it helps you to think about reactions and energies, and it's good for you. Any other questions?
So the gist of it is, you add them up, put everything on different sides, the reactions, add them up, and make sure that basically balance it.
Right.
Everything the same. Add them up, cancel out whatever we
Yep.
need to do, put them together, then
You're combining these, and so we've got the arrow here, and then we add up everything on the left side of the arrow, and we put that on the left side of the arrow. The arrow's a lot like an equal sign.
yeah.
We add up everything on the right side of the arrow, we put it there. Then we, combine like terms, and anything that's present on the left and the right goes away. And then the goal is to end up with a reaction down here that is the same as the requested reaction. And whatever you do to these, you have to do to those. Okay? When you get, we've muddled through several different types of explanations here. When we finally muddle through and come across an explanation that makes sense to you, then you can look at that and say, oh, okay, I see what you're doing. Now, if you stop there, it will be gone tomorrow. Okay? So that's where you have to go and you have to try doing it yourself. You have to do it yourself. And just a reminder, the homework assignments I'm giving you on Mastering Chemistry, I consider those to be the minimum that you should be doing. And that's why I give, as practice, I just started giving all the tutorials that Mastering Chemistry has, because that's a good place to go practice. But you can also use the examples in your book. That's a great place to start, because a lot of them are written out and they show the solution step by step, so you can learn from that as well. but then also the questions in the back where they give you the answers so that you can check your work and make sure that you're doing it correctly.